Concepts. 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 Let R be an integral domain. Let R be an integral domain. And R be an integral domain. And A and B are any elements of R. A, B and elements. So definition. Elements of R. Elements of R. A is said to divide B. A is said to divide B. Or A is a factor of B, or B is a multiple of A. If A equal to B, A are equal to B. For all small r belongs to capital R. Small r belongs to capital R. If A divides B, then we denote this. If A divides B, we denote this. A by B. If A does not divide B, suppose if A does not divide B, then we denote this A cross A does not divide B. So B are here A and B associate and denoted here. A and B associate and we denote this A similar B is similar B. If A equal to B, if A equal to AU equal to B, for some U in capital R. Thank you. Another definition. Another definition. Another definition. Let P be a non-zero and non-unit in an integral domain R. P is non-zero and non-unit in an integral domain R. An integral domain R. Then P is said to be prime element. P is said to be prime integral R and for R a comma B belongs to capital M. So P divides AB. P divides AB. That implies either P divides A or P divides B. P divides B. P divides B. Second one. P is said to be an irreducible element. P is said to be irreducible element. Irreducible element. Irreducible element in R. For any belongs to A comma B belongs to capital R. That equal to P equal to AB implies either A or unit, either A is a unit or B is a unit. B is a unit or B is a unit. In other words, P is called equal. In other words, P is called irreducible. Irreducible. The converse irreducible. P cannot be written as product of two non-units in R. So using these two definitions, we prove one theorem, the most important theorem. Theorem number 4.2.3. 4.2.3. Theorem statement. Every prime element in an integral domain. Every prime element in prime element in an integral domain. Integral domain. Integral domain is irreducible. Class లో ఉన్నాను 11:30కి అయిపోతుంది అప్పుడు కాల్ చేస్తాను. Every prime element is an integral domain. Is irreducible. Every prime in an integral domain is irreducible. Means irreducible. We are on E du. The converse is not true in general. The converse the converse is not true in general. In general. Proof. Let P be a prime element in general. Let P be a prime element in an integral. Prime element, prime element in an integral domain. Integral domain. Domain. That domain. Then by definition, P is non-zero, non-unit in R. Then by definition, P is non-zero, unit in R. At A and B, be any elements of R. At A and B, be any elements in R. Elements in R. Elements in R. Such that P equal to AB. ST means such that P equal to AB. Then P divides AB. Then P divides AB. Then P divides AB. P divides. Since P is prime, P is prime. P is prime. We have that with the P divides. We have that means by definition, P divides A or P divides B. P divides B. P divides B. If P divides A, then PR equal to A. If P divides A, P divides A, then PR equal to A. PR equal to A. For some small r belongs to capital R. Therefore, P equal to A. P equal to A. That equal to PR into C. PR into B. That equal to P into RB. P into RB. Since R is an integral domain, integral domain, R is an integral domain. Integral domain. And P is not equal to 0. P is not equal to 0. We get I equal to. We get I equal to RB. RB. Then that is B is unit. That means B is unit. B is unit. Similarly, we can prove that P divides B and A is a unit. Similarly, we can prove that. Means RTP required to prove that. If P divides B, then A is unit. A is unit. A is unit. Thus, P is reducible. Thus, P is irreducible. IRREDUCIBLE. P is irreducible. So the converse is need not prove in general. The converse need not prove. Need not prove. In general, an irreducible element, an irreducible element an irreducible element may not be prime. May not be prime. May not be prime. May not be prime. To see this, consider the following example. So, this completes the proof. Hence proved.
Sir. In above lines, I is equal to RB or 1 is equal to RB, sir?
Here, this one. I equal to R.
Yes, sir. In textbook, there is 1, sir. In textbook, 1 is equal to RB is there, sir.
1 equal to RB. B, P is it divides. We get RB. Yes, 1 is correct. 1 because prime number, co-prime number, no? Divides.
Yes, sir. Thank you, sir.
Next. Unique factorization domains. Unique factorization domains. 4.3. Unique factorization domains. Unique factorization domains. Factorization domains. Factorization domains. So definition. Definition. An integral domain R is said to be an integral domain. R is said to be said to be unique factorization domain. Factorization domain. Domain. Factorization domain. If satisfies the following conditions or axioms. If satisfies following axioms or conditions or properties. First one, any non-zero element in R, any non-zero element in R is either a unit, or can be expressed as, product of finite number of finite number of irreducible elements in R. Elements in R. Irreducible elements in R. Second one, if P1, P2, etc. Pn, if P1, P2, etc. Pn, that equals to Q1, Q2, etc. Qn, where Pi's, Qj's are irreducible, where Pi's are Qj's are irreducible, then n equal to m. N equal to here P1, P2, Pn, that equal to Q1, Q2, this is Qm. Then n equal to m. And each Pi is an associate. Then each Pi is associate for some Qj, vice versa. Means so on. Next, using this definition, we prove important theorem. That one is 12.3.2. 12.3.2 theorem. Theorem. Statement. Every Euclidean domain is a very Euclidean. Every Euclidean domain is unique factorization theorem. Unique factorization domain. Most important for 10 marks question. Proof. Let R be an Euclidean domain. R be an Euclidean domain. Euclidean domain. With Euclidean map D. With Euclidean map D. Map D. Euclidean map D. We have to prove that 1 and 2 by definition is satisfied. First one. Let A be a non-zero element in R. Let A be a non-zero element in R. Element in R. Non-zero element in R. We use induction on D of A. We use an induction D of A. Induction D of A. So to prove that either A is a unit, we need to prove that. Need to prove that either A is either a unit or A can be expressed as product of finite number. It can be expressed as a product of finite number of irreducible elements. Finite number of irreducible irreducible elements. Note that D of 1. Is less than or equal to D of A. If D of A equal to D of 1. If D of A equal to D of 1. Then A is unit. Then A is unit. So suppose D of A is greater than D. Let D of A is greater than D of 1. D of A is greater than D of 1. Assume that one holds. Any non-zero element. Assume that one holds for any non-zero element X. For any non-zero element X with D of X is less than D of A. Less than D of A. Next case. If A is irreducible, then we are through. If A is irreducible, Then we are through. Then we are through. Then we are through. Then we are through. Let suppose A is not irreducible. Suppose A is not irreducible. Then A equal to BC. Then A equal to BC. For some non-zero units B and C. For some non-zero elements. Zero elements. B and C in R. B and C. B and C in R. B and C in R. So we have 4.2 point. We have B of B is less than B of B less than D of BC. D of BC. That equal to D of A and D of C. D of BC. That equal to D of A. D of A. By induction hypothesis, we get, therefore, by induction hypothesis means given data. Induction hypothesis. By induction hypothesis, we obtain or we get P equal to P1, P1, etc. P1, etc. Pn and C equal to R1, R2, etc. Rn, where Pi's and Ri's are irreducible. Where Pi's and Rj's are irreducible. Then A equal to BC. That equal to, this is not P1, P2. Mistake given. So you have to correct it. B equal to P1, P2, etc. Pn. This is P2. That equal to P1, P2, etc. Pn. R1, R2, etc. Rn. So and therefore A is a product of finite number of irreducible elements. And therefore A is a product of finite number of irreducible elements. Finite number of irreducible elements. Irreducible elements. Only half part will go. Next half part is there. So move next case. Second part. Second one. Let P1, comma P2, comma etc. Pn, that equal to Q1, comma Q2, etc. Pn, where Pi's and Qj's are eligible in R. Pi's and Qj's in R. Qj's in R. Qj's in R. Are irreducible in R. Irreducible in R. Irreducible in R. Irreducible in R. Since R is Euclidean domain, Euclidean domain, every irreducible element is prime in R. Every irreducible element is prime in R. And prime in R. And in particular, Pi's and Q's are all prime. In particular, Pi's and Qj's are all prime. We can suppose that n is greater than or equal to m. Since P1, P2, etc. Pn, that equal to Q1, Q2, Q2, product into Qm, so on, etc. 1 is a co-prime number. So we have that P1 divides P1 divides Q1, Q2, etc. Qm, and hence P1, and hence P1, and Q1 divides Q1 for all J1 lies between 1 and m, 1 less than or equal to J1 is less than or equal to m. So P1 S1 equal to, so that P1 S1 equal to Qj, Qj1, which is belongs to R, which is belongs to R, which belongs to R. So substituting in 1, we obtain, substituting in 1, we obtain substituting in 1, we obtain substituting in 1, we obtain next page one, we obtain P1, P1, P2, etc. Pn, that equal P1 S1, P1 S1. Pi, here pi means product of terms. Sigma means sum of terms. Pi stands for product of terms. J does not belong to J1. Q of J, Qj are not equal to, J is not equal to J1. Since R is an integral domain, R is an integral domain, and P1 is not equal to 0, and P1 is not equal to 0. We get, or we obtain P2, P3, we obtain P2, P3, so on, Pn, that equal S1. So product of means pi means product of terms Qj, Qj. J is not equal to J1, Qj. Now consider P2 and repeat the argument, continues this process. Consider P2 and repeat the argument and continue this process. Repeat the argument and continues this process. Continues this process. P2, P3, Pn. Finally, all the elements P2, P3, etc. Pn. Finally, all the elements on the left. Finally, all the elements on the left, will be exhausted. Exhausted means to vanish, to become zero. Will be exhausted. If n is less than m, then there would be elements. Then there would be elements would be elements. Remind and write of the above equation. Remind on the right. Above equation. This must be unit. Therefore, Qj's must be exhausted. Therefore, Qj's must be exhausted. Exhausted. Simultaneously along with PIs. Simultaneously along PIs. Yes. This is say to n equal to m. Yes, that implies n equal to m. Next is equal to m. Also, this process we get the this process we get PISI equal to 2J. PISI equal to QJ for 1 less than or equal to I less than or equal to n, and 1 equal to S1, S2, etc. Sn. And therefore, S1 is a unit. Therefore, each S1 is a unit. S1 is a unit. S1 is a unit. So that Pi is associate of J. So that Pi is associated of QJ. QJ is associated of PJs. QJ. So this completes the proof. Percentage. Hence the theorem. Next. Exercise 4.12.4.1. 12.4.1. 12.4.1. This is also theorem. Example. Consider statement. Let R be an integral domain. R be an integral domain. And A and B belongs to, and here A and B belongs to R. Then prove the following properties. Prove that first one. A divides B. If and only if. If and only symbol. If and only. B are subset equal to. A R Yeah. Second option. A. Actually, you need to read this is A similar to B. Here we need to consider A associated to B. We have to understand. If and only if. If and only if. A equal to BR. AR equal to BR. Third one. A divides 1. A divides 1. If and only if A is a unit. Is a unit. If and only if A associated to 1. A is associated to 1. Solution. Most important. 5 marks question. So if A by B, A divides B. Then AX equal to B. Then AX equal to B. AX equal to B. For some X belongs to R. Hence, BR equal to AXR. XR. Is subset are equal to AR. Subset are equal to AR. Conversely, if BR subset are equal to AR, yeah, then B equal to B1. That implies BR belongs to BR. Is subset are equal to AR. Hence, B equal to AX. For some X belongs to R. So A divides B. Second solution. A associated to actually A similar to B means A associated. We have to consider here A associated to B. A divides B. And B divides A. If and only if AR subset are equal to BR. And BR subset are equal to AR. If and only if AR equal to BR equal to BR. Third option. Third one. A divides 1. If and only if AX equal to 1. For some X belongs to R. So if and only if A is a unit. is a unit. A is a unit. If and only if A is associated to 1. 1 since 1 divides A. 1 divides A is true for A. Is true for A. True for A. Hence the solution. This completes the solution. Hence the solution. Right. So these are all what we discussed in the last 7th, 8th, 9th, 10th, 11th, 12th, all 6 units. Those are all. If you study those well, you will get 50 marks. Means 80 marks question paper, no? Your theory. 40 marks you will get easily. Okay? All of you. Thank you very much. I'm leaving. Okay, all of you listen. Are you audible?
Yes, sir.
Yes, sir.
What we discussed last the 6 units. 7th, 8th, 9th, 10th, 11th, 12th. Out of 80 marks is your question paper, 50% you will get. Okay, thank you. I'm leaving. Thank you. I wish you best of luck.
Thank you, sir.